A very good day, everyone. In this lecture, we'll cover the basic operations of operational amplifiers. In our last lecture, we actually provided a brief introduction on operational amplifiers and went on to discuss the basic configurations of the op-amp. That is, when the voltage source is connected to the negative terminal, that is the inverting terminal of the operational amplifier, then we said that such configuration is the inverting op-amp, such that we have something like this. This is the inverting terminal, this is the non-inverting terminal. So should we have the voltage source connected to this terminal, say this is B sub S, and this is the series connected resistance. Here we have the output. So we said this configuration is the inverting op-amp. And the second configuration we talked about, and just to re-emphasize, we were able to figure out the closed loop voltage gain, which is the ratio of the output to the input voltage. And here we saw that it was the inverted or inversion, where this negative sign denotes the inversion, sign that is negative of the feedback resistance, the ratio of the feedback resistance to the resistance R1 connected at the input side. And the second configuration was such that the voltage is connected to the positive terminal, or better still, the non-inverting terminal of the op-amp. And then we said such configuration was the is the non-inverting op-amp. And there we drew something like this. Here we have the series connected resistor. I recall we said this models the Thevenin equivalent circuit, where the voltage source is connected in series with the resistance value. And then we have something like this, for which this is the output voltage. And there we also were able to figure out the closed loop voltage gain, which was given as the output ratio of the output voltage to the input voltage. We saw that it was the same as R1 plus the feedback resistance divided by R1, which happened to be the same as 1 over RF over R1. Okay. But this time, we are going to delve into, investigating, or better still, discussing a few operations of the op-amp. Okay, and let's say some of the operations of the op-amp. So the first of which is integration. Okay, and here the op-amp integrator is usually useful in performing mathematical integration. Okay. Okay, and they are usually useful in converting between square wave signals to triangular wave signals, and also they're also useful for converting triangular wave signals to say sine wave signals, and also useful for converting sine wave signals to cosine wave signals. Okay. So another operation is where we're going to describe the circuit shortly, is the is for differentiation. Okay, so we have the differentiator op amp, and the op amp differentiator is often designed to operate on rectangular and triangular wave signals, and then waves or signals rather, and they are commonly used as wave shaping circuits, and also high frequency component detection in a given input signal. And one other operation we're going to be looking at right quick is the summing circuit, okay, or better still the adder. Okay, and the summing circuit is commonly used in audio mixers and a whole lot of circuits where we have to combine quite a number of signals to generate a single output. So let's look up the integrator op amp. So for the integrator op amp, we have something like this. There is this store value is connected to the inverting terminal. Here we have the output V naught. Then we have a capacitor connected feedback. So where this is the feedback capacitance, and then you have the input voltage, and then here is the output voltage. And then the non-inverting terminal is connected to ground. So let's just get this to ground. So let's get this to ground. So where this is severe reference voltage, which is 0 voltage, meaning for ground connection. This is the non-inverting voltage, V sub P, and the inverting voltage, V sub N, which are node voltages. Okay, now in this circuit, the output of the circuit will be seen shortly to be the integration of the input voltage. So to begin, let us quickly recall the basic assumptions, okay? Assumptions. So we have first the current constraint, which is I sub P, same as I sub N, is 0, meaning that no current flows through the terminals of the op amp. So that is I sub N is equal to 0, and the current through this terminal, I sub P, is equal to 0. Okay? And then we have the voltage constraint, which is V sub P is the same as V sub N. Okay? And in this case, V sub P is connected to ground, which is 0. So that implies that V sub P is equal to 0, and V sub N is the same as V sub P. That will be equal to 0. Now, based on the current constraint, you will observe that the current, that is I sub T, that that is I of I sub t, and there's a current flowing through the resistor. R will be the same as the current flowing through the capacitor. So this current will be the same current flowing, because at this point no current is flowing through this terminal because I sub in is equal to 0. So the entire current will flow this way. Okay, so it means that I sub I of t being the same current flowing through the R resistor will be the same current flowing through the capacitor C. Okay, good. Now, if that is taken, we already established that this voltage value is 0. So if we write Ohm's law at the input side, then we should be able to investigate or better still estimate the value of I sub I of t. So now by Ohm's law, now the current flowing through the resistor, R, then the same current flowing through the capacitor, which is I sub I of t, will therefore be the same as the difference between these node voltages divided by the current. That is, by passive sign convention, this is positive, this is negative, so that will be V sub I of t minus V sub n divided by R. But V sub n is the same as 0 because the voltage V sub p is equal to 0, and by the voltage constraint assumption, V sub p and V sub n are the same, and that is the same as 0. So this therefore implies that V sub I of t minus 0 divided by R. So I sub I of t will be the same as V sub I of t divided by R. So let's say this is our first equation. Now, by Ohm's law also, by Ohm's law, we can equally write the current flowing through the output side of this configuration, and that will be I sub I of t. Okay, and hence the current flowing through the capacitor I sub I of t will be the same as C dt V sub n minus V naught of t. V sub n minus V naught of t. And we already know that V sub n is the same as 0, okay, based on the voltage constraint. Since V sub p is grounded, such is the same as 0, then V sub n is 0, then I sub I of t will be the same as negative C the V naught of t dt. Perfect. Now that we have established that, then should we call this equation 2? You will observe that equation 1 and equation 2 are the same because that is the same current flowing through. So since equation 1 and 2 are comparable, therefore V sub I of t, V sub I of t over R will be the same as negative C dV naught of t dt. And if we integrate both sides, so that will give us integral V sub I of t over R will be the same as negative integral c dv naught of t dt. So let's extract this through. So this is going to give us integral v sub I of t over r with negative c integral dv naught of t dt. And once we take the integral of a differential value, so we're going to get v naught. So here we now have integral v sub I of t over r will be the same as negative c v naught of t. And hence, v naught of t will be the same as negative 1 over c r, we'll bring the resistor r, integral v sub I of t dt. Okay? So once we integrate, yeah, this will be with respect to t, dt, right? So we have dt, dt, okay. That's fine. Good. Now, you'll observe that the CR, or better still RC, whichever way you place it, is the gain constant. And in the S domain, we can actually place the transfer function or the system function. So, system, or better still, transfer function in the S domain, which is equivalent to the Laplace transform, to the V naught of X, that is the output, the ratio of the output to the input, will give us negative 1 over RC, right? Which is the same. Then S. Now, note that, better still, note that 1 over S is the same as the integrator. Okay? This integrator. Okay? Is replaced by 1 over S. And the corresponding frequency domain representation will be the same as V naught j omega divided by V sub I j omega, which is the same as negative 1 over j omega RC. Perfect. So let us look up the differential operational amplifier. The differentiator Op. So in this case, we have the capacitor connected to the inverting terminal of the op amp. This is V naught of T, the output, and then resistor is connected at the feedback point. That's the feedback resistance. So here we have the input voltage. So this is the non-inverting voltage. This is the inverting voltage. Okay. And recall the assumptions for current constraints. Current constraints. We have no current flows through the terminals, that's 0. And then for the voltage constraint, we have the non-inverting voltage is the same as the inverting voltage. And also, the current I sub I of t flows through the capacitor will be the same flowing through the resistor because no current flows through this terminal. So I sub n is 0 and I sub p is 0. So the current flowing through is actually I sub I of t. Okay. So by Ohm's law, we can actually write the current at the input side of the circuit, which is I sub I of t will be the same as C d dt, the voltage difference between these 2 points, between this point and this point. These are the 2 nodes. Yeah, so that will be V sub I of t minus V sub n. And we already know that the reference value here is 0 since the non-inverting terminal is grounded, and by the voltage constraint, V sub P is the same as V sub N, and now it is same as V ref, which is equal to 0. So means this value reduces to 0. Then I sub I of t will be the same as C dV sub I of t dt. So here's the first equation. And in a similar vein, if we write Ohm's law at the output side of this circuit, then by Ohm's law, so the current flowing through the output region will be the same as I sub I of t, which would be the voltage value divided by the resistor. And the voltage value will be the voltage difference between the 2 nodes, V sub n, that will be V sub n, minus, because by passive sign convention, positive, negative, so V sub n is positive with respect to this terminal, and V naught sub t is negative with respect to this, minus V naught of t divided by the feedback resistance. And we already know that V sub n is the same as 0. So since it's grounded, so this reduces to 0. So hence, I sub I of t will be the same as negative V naught of t divided by R sub f. So this will give us a second equation. And now you observe that the 2 equations are comparable. So since equation 1 and 2 are comparable, so what we now have to do is to combine them. So that is C dV sub I of t. The t is the same as negative V naught of t divided by R sub f. Okay, now V naught of t will be the same, cross multiply here, will be the same as negative R sub f of c dV sub I of t dt. Okay, and here R sub f of c is the differential gain constant. This is differential gain constant. So from here. So in the S domain, the system function, or better still, or the transfer function will be the ratio of the output to the input voltage. That will give us from this point here, that will give us negative feedback resistance, CS. In this case, S is the same as the differentiator. While in the frequency domain, that'll be V0 J omega divided by V sub I J omega will be the same as negative. Now recall that S is sigma plus J omega. Now this reduces to 0 in this case, so J omega, so S reduces to J omega, negative J omega, R sub F. See, well, you may want to review the videos in signals and systems, have them up in the channel, so you could revise Laplace transform, Fourier transform, and the likes. So that's it for the differential, but I said the differentiator op amp. So now we have another operation we want to talk about, which is the summing op amp. Now for the summing op amp, or better still the adder, we have two variants, the inverting adder or summing op amp and the non-inverting adder, or better still summing op amp. Okay, so let's begin with the inverting summing op amp. For the inverting summing op amp, so let's say we have two resistors connected to the inverting terminals, or the inverter terminal of the op amp. So we have, this is V1, V2, this is R1, this is R2. Then there's the output, V0. Then we have the feedback resistance, R sub F. Now, the non-inverting terminal is connected to ground. So VRF here is equal to 0 volts. So this is the non-inverting voltage, and this is the inverting voltage. And as always, we can equally evoke the assumptions that I sub P is equal to I sub N is equal to 0. No current flows through the terminals. And then the voltage constraint, V sub P, is the same as V sub N. Okay, in this case, V sub P is grounded. So V sub P is the same as V sub N is equal to 0. Okay, perfect. And also, you see that the current flowing through this resistor is I1. Current flowing through this resistor is I2. And the sum of the currents by KCL, current flowing through a node, will be the same as the current flowing out of that node is I. Now, by the current constraint, the current flowing through this terminal, I sub N, is 0. So hence, the entire current, I, flows through the feedback resistor. I. Okay, so it's the same current because I sub P is equal to 0. Okay, so by KCL, by Kirchhoff's current law, the current flowing out of a node is the same as the sum of currents flowing into that node, I sub 1 plus I sub 2. And then by Ohm's law, this expression we therefore reduce to I being the same as I sub 1 will be V sub 1 minus V sub n by passive sign convention, positive, negative, right? So that will be I sub 1 will be V sub 1 minus V sub n, is node voltage, divided by R sub 1 plus V sub 2 minus V sub n divided by R2. Now, since V sub n is the same as V sub p is the same as 0, so this reduces to 0, this also reduces to 0. So I is the same as V sub 1 divided by R1 plus V sub 2 divided by R2. Okay, now let's see this first equation. Now, by Ohm's law, at the output side of this configuration, so let's say by Ohm's law, then the current at the output, which is the same as I, will now be V sub n minus V naught, V sub n minus V naught divided by R sub f. Now, V sub n is the same as 0, right? Because we already established that based on the constraint, and V sub p is grounded, so V sub n is 0. Such that I, the current flowing through the feedback resistor, is the same as negative V naught divided by R sub f. So this is our second equation. Okay. Now, since equation 1 and 2 are comparable, then V sub 1 divided by R1 plus V sub 2 divided by R2 will be the same as negative V sub V naught divided by R sub f. Then, now if we rearrange this, then V naught will be the same as RF, that is negative, of RF divided by this, and then RF divided by this, so that will be RF divided by R1, V1, plus RF divided by R2, so. So from this, we can actually come up with a little conclusion that let's say for n number of resistors connected to the inverting terminal, then we can as well say that V naught will be the same as negative RF over R1 V1 plus RF over R2 V2 plus all the way to plus RF over Rn Vn, such that when RF is the same as R1, is the same as R2, is the same as all the way to Rn, so it means they will all reduce to unit values, such that V naught will be the same as V1 plus V2 plus all the way to plus Vn. Hence, the output voltage V naught, this will be negative, please, the negative sign, okay? Hence, the output voltage is seen to be the sum of the phase-shifted input voltages, because this is negative V1, negative V2, negative all the way to negative Vn. So these are all phase-shifted, okay? So the negative values accounts for the 180-degree phase shift, okay? Which implies the inversion, okay? Hence, inverting other or summing op arm. Okay, so now let us consider the non-inverting summing operational amplifier. So in this case, we have the this is V1, V2, this is R1, this is R2. It's connected to the non-inverting terminal. And then in this case, we have the feedback resistance here. So F is grounded. Let's say this is, let's say R. Okay, and this is V naught. Okay, so we can as well evoke the assumptions for the current constraint. Now this is V, this is negative here. This is V sub n, and at this point is V sub p, right? So I sub n is equal to 0, then I sub p is equal to 0, right? Now, the voltage constraint is such that V sub p is equal to V sub n. Okay. Now, the current flowing through R1 is I sub 1. Current flowing through I2, R2 is I sub 2. Then I flows out of this node. That's I. Okay. Now, since I sub n is 0, so no current flows through this terminal, and I sub p is 0, no current flows through this terminal. Hence, the entire current will flow all the way. That's I, right? Okay. So, by KCL at the input, then the input current, I, will be the sum of I sub 1 and I sub 2, meaning the current flowing out of this node, I, is the same as the sum of the currents flowing into the node, which is I sub 1 plus I sub 2. And by Ohm's law, we have I to be the same, I sub 1 V sub 1 minus V sub P, V sub 1 minus V sub P divided by R1 plus V sub 2 minus V sub P, V sub 2 minus V sub P divided by R2. And then this gives us V sub 1 divided by R1 minus V sub P divided by R1 plus V sub 2 divided by R2 minus V sub P divided by R2. Okay. But at this terminal, no current flows through. So I sub P is 0. So hence, we can conclude that I sub P is equal to I sub N is equal to 0. And now we know this I is the current flowing through the terminal, which is the same as I. So hence, this expression can be equated for 0. So I sub 1 divided V sub 1 divided by R sub 1 minus, okay, that is V sub 1 divided by R sub 1 minus V sub P divided by R sub 1 plus V sub 2 by R sub 2 minus V sub P divided by R sub 2 is equal to 0. So I need to maximize this space. Okay. Now, if that is clear, it means that from the foregoing, then we can actually show that V sub 1 divided by R sub 1, yeah, plus V sub 2 divided by R sub 2 is the same as V sub P that crosses the equality sign divided by R sub 1 plus V sub P divided by R sub 2. And if we take the LCM in both sides, so this will be R1, R2, this will be V sub 1, R2 plus V sub 2, R1, then it will be equal to R1, R2, so this will be V sub P, R2 plus V sub P, R1. Okay, now this part is the same as this part, so it can cross each other. So that we now have V sub 1 R2 plus V sub 2 R1, as this expression is the same as this expression here, V sub P R2 plus V sub P R1. So let's try this one. Then V sub P is common here, so V sub P will be the same as V sub 1 R2 plus V sub 2 R1 divided by R2 plus R1, R2 plus R1. So let's say this is our equation star. Now, if we consider the current flowing through the feedback resistor, that is the output side, then we can equally apply Ohm's law by Ohm's law at the output. Then I will be the same as V0 minus Vn. V0 because this is the current direction, so it's flowing from this point to this point, so minus V sub n divided by R sub f. Okay, and by the voltage constraint, V sub p is the same as V sub n, so we can replace this. So I therefore, and I therefore will be the same as V0 minus V sub p divided by R sub f. Okay, so let's say this is equation K1. Now you observe that no current flows through this terminal, so the entire current will flow in this direction, which is also I, because the current in this through this link here or terminal is 0. I sub n is 0, so the entire current flows through R to ground. Okay, now if that is clear, then similarly, right, I, this branch here, I will be the same, this V sub n here, right? V sub n, why this is Vref, V sub n minus Vref divided by R. Now we know Vref is 0, this is 0 volts, right? Because it's grounded, that terminal is grounded. So I here will be V n sub n divided by R. So let's say this is K2. Now, K1 and K2 are comparable because it's the same current flowing, such that since K1 and K2 are comparable. Therefore, V0, which is this expression, minus V sub P by R sub F is the same as Vn. In this case, is the same as Vp, right? So we can replace it as this same case. I is the same as V sub P divided by R, because Vn is the same as Vp by the voltage constraint. And say Vp divided by R. Okay. And now, this is the same as saying V0. Well, let me break this again. Over, that's V0 over RF, R sub F, minus Vp divided by R sub F is the same as V sub P divided by R. Okay. And now, if we collect like terms, so V0 divided by R sub F is the same as negative return positive Vp V sub P divided by R sub F plus V sub P divided by R. So V0 now is the same as V sub P times this. This is R. So let's take the LCM for instance. V0 divided by R sub F. So that's R sub F R. So that would be Vp R plus Vp R sub F. Yeah. And now this part we truncate this part. So it means V0 is the same as V sub P R plus V sub P R sub F divided by R. Okay. Now, this is the same as writing V0, that's R plus R sub F divided by R, all enclosed Vp. So in this case, V sub P is the same as, if we divide this by this, then making V sub P the subject of formula here. So that will be V0 R divided by R plus R sub F. Okay. So let's make this next equation, let's say V. Okay. So now we can compare equation star with equation V, because they are both V sub P. And once we do that, then we are going to have V sub 1 R plus V sub 2, that's R2, R1, then divided by R2 plus R1 will be the same as V0 R divided by R plus R sub F. And here can make V0 the subject of formula. Okay. And then this will multiply this. So that will be V sub 1 R1 plus V sub 2 R1 R plus R sub F divided by R2 plus R1 times R. So if we open this up, so V0 is going to give us that's this times this, that is V1 R1 into bracket R plus R sub F plus V2 R1 into bracket R plus R sub F, then divided by R into bracket R2 plus R1. Yeah, so I think things are getting a little interesting now. So at this point, we can actually separate these, which will now be the same. Now V0 will be the same as R1 times all of this, right? This is V1, this is, okay. Oh, we have not messed up something here. This is R2. It's V1, R2, V1, R2. So this is V1, R2 coming from V1, R2. That's V1, R2. Yeah, V1, R2, V2, R1, V2, R1. Okay, I think everything is in good shape now. So then we have R2 into bracket R plus R sub F divided by R into bracket R2 plus R1 V1 plus R1, right, into bracket R plus R sub F over R2 plus R1 all equals R V2. And this is the same as V0. Okay, now when R1 is the same as R2, is the same as R, is the same as R sub F, then this expression will reduce to unity such that V0 will be the same as V sub 1 plus V sub 2. So this is the non-inverting summing op amp. So let us consider a simple example. Say we have okay, 3 resistors here, 3 resistors. Connected at this node. I think so. Okay. So now we have this connected to the non-inverting branch, or the inverting branch rather. This is V sub n. Then non-inverting branch is connected to this resistor, then is connected to another voltage value. So here we have the feedback resistor, and then this again is connected to some other to ground. Okay, this is fine. So here we have V sub 1, which is the same as 100 millivolts. Now V sub 2 is the same as 200 millivolts. And V sub 3 is the same as 300 millivolts. Okay. So we have R1, which is the same as 5k ohms. R2 says 10k ohms. And R3 says 20 k ohms. Now we have R4 here. Let's say this is 15 k ohms. And then we have R5. Let's say this is 2 k ohms. Then we have V4. So this is 3 volts. Then this is the load resistor. Let's say this is 8 k ohms. So here we have V0, right? So in this case, we want to compute, we want to evaluate I sub 4. So there's I sub 4, the current flowing through this, I sub 4. So what is I? 4. And then this is I naught here. This is IL. And this is I sub 1. This is current flowing through the to this resistor R2. And then this is I sub 3. So total current flows out is I. Okay. And then we also want to evaluate I naught. And then we also want to evaluate I sub L, current flowing through the load resistor, 8 k ohms. Now we know, based on the assumptions for an ideal op amp, that no current flows through the terminals. So I sub N is equal to 0. Then I sub P is also equal to 0. Okay. And then we have the voltage constraint, that V sub P is the same as V sub N. Okay. Okay. Now, based on the current constraint, we can as well conclude that no current flows through this terminal. So the current I flows all the way, right? So I, in this case, is the same as I sub 4, since I sub N is 0. And this is a node. So if no current is flowing through this part of the circuit, then the total current flows through. So meaning I is the same as I sub 4. Now, if that is clear, then we already know that I is the same current by KCL. The current flowing out of this node is the same as the current flowing into the node. So I sub 1 plus I sub 2 plus I sub 3. Now we know by the current constraint, I sub N equal to 0, I sub P equal to 0, so I is the same as I sub 4. Now, if that is clear, then by Ohm's law, can rewrite this expression so that I sub 1 will be V1 minus Vn, because this node here is Vn, yeah, so V1 minus Vn divided by R1, plus then I2 will be V2 minus Vn divided by R2, plus I3 will be V3 minus Vn divided by R3. Good. But we know that Vp is the same as Vn, the voltage constraint, and we know that this is Vp here, and Vp is the same as V sub 4. Okay, so it means that Vp is the same as Vn is equal to V sub 4, and that's the same as 3 volts. Okay, just given. So hence, this is the same as I sub 4. So I sub 4, therefore, will be the same as 3 volts because Vn is the same as Vp and is the same as the 4 volts, right? And we know V1 is 100 milliampere, which is 0.1 volts. That will be 0.1 volt minus 3 divided by R1, which is 5K, that is 5,000, plus V2, which is 200 millivolts, which is the same as 0.2 volts, 0.2 volts, minus Vn. Vn is the same as Vp, which is 4 volts, which is the same as V sub 4. V sub 4 rather, not 4 volts, 3 volts, V sub 4, which is 3 volts, minus 3, divided by R2, 10,000, 10K, then plus V3, which is 300 millivolts, which is 0.3 volts, 0.3, minus Vn, minus Vn, which is the same thing as Vp, which is the same thing as 4 volts, sorry, the same thing as 3 volts, which is V sub 4, that's minus 3 divided by 20K, that's 20,000. Good. And now this is going to give us negative 2.9 divided by 5,000 plus negative 2.8 by 10,000 plus negative 2.7 divided by 20,000. Now this is going to give us negative 0.0005A plus negative, this is 2.8, right? 0.00028 plus negative 0.000135. Yeah? Now this is going to give us negative 0.000995, which is the same as negative 0.995 milliampere. That is I. Now we have I naught, okay, and IL, right? Now, by way of investigation, we know that IL by Ohm's law, I sub L, which is the current through the load resistor, is the same as V naught divided by RL. Okay, and also by Ohm's law, the current at the output side, which is I sub 4, is the same as V sub n minus V naught, V sub n minus V naught divided by R sub 4. Okay. So from this point, if we cross multiply, that is I sub 4, R sub 4 is the same as V sub n minus V naught. So that this V naught is the same as V sub n minus I sub 4, R sub 4. Now, by the voltage constraint, we already know that V sub p is the same as V sub n is the same as V sub 4. Okay? Which is the same as 3 volts. So that V naught will be the same as 3, V sub n is the same as V sub 4, which is 3 volts, minus I sub 4, we already know, which is minus 0.000995 times R sub 4, which is 8K, which is 8,000. So this is going to give us 3 plus 14.925. And V naught will be the same as 17.925 volts. Now that we know this, recall this expression here, which already established by Ohm's law. Then I sub L will be V naught, which is 17.925 volts, divided by R sub L. R sub L is 8K, which is 8,000. Yeah, and that's going to give us 0.002241. So I sub L, the current flowing through the load resistor, will be the same as 2.241 milliampere. Okay, sorry for all of these mappings. Okay, and then to evaluate I sub naught, which is the output current, I sub naught. Now by KCL, the current flowing into this node is the same as the current flowing out. So I sub L is flowing out is the same as the current flowing in, I sub 4 plus I sub naught. Okay, and then I sub naught will be the same as I sub L minus I sub 4. So we already know that I sub L is the same as 0.002241, which is this, minus I sub 4, which is minus 0.000995. Yeah, so this is going to give us 0.002241 plus 0.000995, and that's going to give us 0.003236. Therefore, the output current is the same as 0.236 milliampere. And I think this is a good place to stop. I will pick things up from here in our next class. Bye for now.